All right, we're here. The crescendo of our course, the fundamental theorem of calculus. This is what we've been thinking about for the last couple of videos, and also by the name of it, it seems like it's a pretty important result for this course. And it is. It's going to tie together a lot of what we've been talking about. What we're going to finally do is really investigate this connection between antiderivatives and areas. The way that we're going to do that is we're first going to start off with defining these area functions using our idea of what a definite integral is. And then we're going to try and differentiate these area functions. We'll find out what is the derivative of these area functions. And that should lead us into both parts of the fundamental theorem of calculus. Part one will set up a general idea of how antiderivatives work with these definite integrals. And part two will connect that really nicely into how we actually will evaluate areas under curves when they're tricky to evaluate because we have non-straight edge functions. All right, so let's first start off with this idea of an area function. We've got a function that's going to be continuous for t greater than a. One of the things to note here is that we're going to be talking about f of t. So this axis that we would normally think of as the x-axis is the t-axis, and we've got f of t up here for our y-axis. Our area function then has an x input variable, but notice that this x input variable is up in the limits of integration here. That's kind of strange. So the area function for f with the left endpoint a, we can pick that to be some number, doesn't really matter, is this integral from a up to x, a moving endpoint, a variable endpoint, under the function f of t and then dt, where again x is greater than or equal to a. This condition is relatively loose eventually, but that's going to be kind of circular. But well, anyways, we'll leave that. We'll just say, for now, this area function is our integral from some starting point up to a variable ending point under this whatever curve it is, f of t dt. Just like we would think, this integral gives the net area of the region bounded by the graph and the t-axis on this interval. So what we have here is that a is some starting point. Maybe I'll make it 1 for now. So if we start things here, maybe what I can say is, in our case, a of x, we'll define it as an integral from 2 up to x of f of t dt. And that means that we can evaluate different areas based on some different ending point. For instance, what I've shaded in here is a of 4, because it's this definite integral from 2 up to 4 of f of t dt. And I could go ahead and I could shade in all the way up to 6. And suddenly this is a of 6 because it starts our area. Oh, I started it at 2. Look at that. I'm supposed to be writing 1 here. I don't know what I'm on. Here we go. It's our integral from 1 up to 6 of f of t dt. Now, since I don't know what any of these sizes are, I actually don't know what these area function outputs are. But whatever they are areas, right? We could go ahead and add in a little bit more all the way up to here, include all of these pieces, and we have a of 8, which is our integral from 1 up to 8 of f of t dt. Cool. We could redefine our area function and change the starting point if you'd like. And now we'll start things at 2. And if we change this starting point, maybe I'll call this one b actually. Sometimes people will use subscripts. They'll call this one like A1, and this one would be like A2 because that's our starting point. But now we could say, all right, b of 4 is our integral from 2 to 4 of f of t dt. It would just be whatever this area here is. So we know that this is going to be negative because we're talking about net area, and this whole region that I've shaded in blue is underneath the t-axis. I could do, again, b of 6 and say this is my integral from 2 to 6 of f of t dt, and that would be this region from 2 to 4 plus this region from 4 to 6. And then similarly, I could do b of 8. That's my integral from 2 to 8 of f of t dt. And that would be this integral here from 2 to 4, the integral from 4 to 6, and then the same thing from 6 to 8. I don't know what these areas are, but if I was able to maybe have some information about these, then I could actually evaluate these little area functions under here. Now, these area functions aren't terribly interesting in and of themselves. What these are going to be are just like tools for how we actually are going to build up to the fundamental theorem of calculus. So I'm not too worried about actually manipulating these and playing with them to find actual outputs. All I really care about is this general idea that as we increase x here, we move through this interval. Maybe I'll start this back at 1 again. And we might shade in this region here. And that's our function at 3. And if we change our function's input, maybe what we're doing is we're just changing the amount of area that we're including in this, because we keep moving our ending point further and further and further as x increases. So that's what this function's doing. Sometimes people will call it an area eating function, because as it moves throughout our function, it gobbles up more and more area under the curve. So if we can understand the general idea of this function, then we can start working with it in every way that we need to. What we're going to really care about is the derivative of this function. And this is kind of a wild thing. When we think about the derivative of this, we want to really get an idea of what we're talking about. We're trying to figure out the instantaneous rate of change of our area function as x changes. Now, if we go back to the definition, this highlighted x in our limit of integration, that's the thing that's changing. Notice we're not changing our function f of t. We're not changing t at all. All we're changing is the end bound of this definite integral. So what we're doing is we're saying things like, all right, maybe we've got this integral function, and if I want to know a prime of 5, I want to know the instantaneous rate of change. What happens if I change this input just a tiny bit? We could say by a differential dx, right? What happens if you change by some infinitely small x value here? And we're not looking at the rate of change of the function. We're not saying, oh, there's almost a horizontal tangent line here, so maybe the rate of change is 0. No, that's not what we're talking about. We're talking about what's the change in area under this curve. And here we can see that by this little red line, we're adding a little bit of area. So we would expect that there's a positive rate of change at this point. Similarly, if we went back to maybe the x value of 3, so maybe I'll say this one is positive. If we looked at a prime of 3, though, and we look at what happens when we change x a little bit, we push it a little bit further, notice this little red sliver that we're adding is a negative area, because it's underneath the the t-axis. And so here we would say maybe this rate of change is negative. Even though it looks like the slope of our function is a bit positive here, right? Our tangent line is positive. That's not at all what we're considering now. So this is a very strange derivative to try and get our hands on, because we're not looking at how this black curve f is changing. We're looking how the size of the area is changing. All right, and we can do this by doing some estimation. You can actually jump right into the limit definition of this if you'd like. We need a little bit more than what this introductory class does, but if you look at this limit as h goes to 0 of a of x plus h minus a of x all over h. Now we can just kind of think about this for small values of h, but what we'll do in a limit is make h get infinitely small, right? Make it go to 0. We can use the definition of our area functions, and we get the limit as h goes to 0. This is an integral from a up to x plus h of f of t dt. Minus a of x is our integral from a to x of f of t dt. And then this is all over h. There's a nice property, though, of integrals that says you can subtract these things. Oops, I want my limit first. And we'll get a limit as h goes to 0 of the integral from x up to x plus h. Now, what this is really saying is, what's the excess amount of area that we've added, right? That's our change in area. It's not the area from a up to x and from a up to x plus h. It's just this extra stuff. So if we're looking at this as an actual amount, there's x plus h, and h is this tiny little width here. And so we just want to know, what's this extra area? The main thing that I want to show you is that this does not depend on a or f of a. What I mean by that is that in the picture I've drawn, I'm starting things at 1. I could change this picture and start things at 1.5. And it doesn't change this extra area that I've added. I could change this picture and start things at 2. And it doesn't change this extra area that I've added. Because again, we're only looking at what happens when the end of this interval gets moved. And so we're looking at what's the excess area. Now this changes the total amount of area when I tinker with this beginning, this left endpoint, but it doesn't change this red change in area. Big difference, meaning our derivative of the area function does not depend on what amount of area we have at the very beginning based on the height of our function or the width part, the input that we're starting things at. Instead, what it depends on is the height of the function at the moving endpoint. You can see that at 3, our derivative was negative, and we knew that because our function value, f of 3, was negative. The height here was negative, and we said, oh, okay, if we have the function being under the curve, that means we're going to be adding negative area, so our rate of change of the area, the signed area, is going to be negative. Similarly, over here at 5, we had a positive function value for f, and so when we added a little bit of area here, it was all positive area. You can also see that it's going to really depend on the height of our function. If we go way out here to like 8 or 9, our function is very tall, and if we add this infinitely thin sliver of area, or maybe just very thin sliver of area, that's much more area getting added. It's positive because our function value is positive, but also because our graph of our function is very tall here, we're adding in a really tall sliver of area. So we might say that the area derivative here is more positive than it is at 5. That's a bit of a weird concept. You can play with this expression if you'd like, and especially if you get past this course and then you go back and rigorously prove everything in like an analysis course, it is not too hard to prove that this just is the function value at x. So this limit ends up giving us a prime of x is equal to f of x. What this means is that the rate of change of this area is solely dependent and equal to the height of the function that we're looking at the area under at the variable endpoint that we're changing. That's a bit of a weird concept. You might want to pause the video, go back, watch that section again, just to really try and make sure that we can see what's happening here, because that's a bit strange. The rate of change of area under the curve is solely dependent on the height of our curve at the point that we're moving to change the area. Not at the beginning point. Here, it's at our end point of our interval. All right, I'm going to move on. We're going to use this idea to prove the fundamental theorem of calculus in 2 parts. The first part is going to really just be that statement that we had, that the derivative of the area function is equal to the height at the ending point, and then we'll restate that in a nice way that will prove a beautiful second part that we'll get at. So here's the first part of the fundamental theorem of calculus. I normally abbreviate this FTOC because I'm lazy when I'm writing things on a board. So if f is continuous on this closed interval from a to b, then the area function a of x that we've defined here from a up to x, where x is in this interval, blah, 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 is continuous on the closed interval, and specifically it's differentiable, meaning the derivative exists on that interval, and the derivative is exactly what we just said it was. It's the derivative of this weird integral with this moving ending point, because that's the variable that's changing, and we said that was equal to the height at the ending point. So this is restating that observation that we were making. We didn't prove this. You can prove it if you go back to this integral over this h with the limit as h goes to 0. You can use the mean value theorem, and then you can do some bounds on this and kind of do like a squeeze theorem on this to show that eventually this limit actually is equal to f of x. So this isn't a full proof, but it's at least a setup and some hints, and then the rest of that is a little bit beyond the scope of the course that we're teaching right now. The big note that we're going to make is that if the derivative of a is equal to x, that literally is a definition of what an antiderivative is. So this tells us that our area function is an antiderivative of f. We used to say that capital F of x is an antiderivative of f if capital F prime is equal to little f. And that is exactly the relationship that we've got here, right? So what we can say now is that a of x is one of the antiderivatives. We can come up with the family of antiderivatives pretty easily from there, and that's what we're going to use to prove the second part of the fundamental theorem of calculus, which is more useful for us. This first part of the fundamental theorem of calculus proves essentially that if you have a continuous function, an antiderivative of that function exists on the interval that it's continuous. We'll come back to that later. Here's the second part of the fundamental theorem of calculus. If your function is continuous on this interval, and you know an antiderivative of that function on that interval, then the definite integral from a to b of f of x dx, the area under the curve, or the net area under the curve, from x equals a to x equals b, is just that antiderivative function evaluated at b minus the antiderivative function evaluated at a. Notationally, this gets used a lot. You've seen this vertical bar probably before. The vertical bar literally means evaluated from x equals a to x equals b. Oops, not parentheses, quotes. And that means plug in b first, a second, and subtract. This seems surprisingly easy. If this is actually true, then this is a very easy way of finding areas that we weren't able to find very nicely using Riemann sums, because remember, to do it using Riemann sums, we had to set up a limit as n, the number of rectangles we used to approximate the area, went to infinity, and that's tricky. But if we can just antidifferentiate the function, then we can just evaluate the antiderivative. So let's prove this thing. So let's start off with just the assumption that f actually is a continuous function, and then we'll define our area function the way that we defined it earlier. So all this to say, everything's set up the way that it probably should be. We've got a continuous function, because we know that if we didn't, the theorem doesn't even apply, and we have the area function that we've talked about this whole video so far. So what we found earlier was that this area function is, in fact, an antiderivative of the function f on that interval from a to b. So that means that we can find a general form of any other antiderivative. There's always some constant that will link every other antiderivative back to this area function, right? We know the family of antiderivatives is this capital F of x plus c. So we have an initial value. Whoops, let me get rid of this. There we go. This is probably supposed to be like a colon or something like that. I don't know. I'm sloppy with my notes today, apparently. We have just evaluating this at x equals a. We'll just say throw a into this, and this is what we get. Now, by the definition of this area function, we said that it was the integral from a up to x of f of t dt. And so what we're going to do is just plug in a for x. Now this should be an easy integral to find, because what this is the area under a curve from a point to itself. If this is A, then we're looking at this area here. Now you can think about Riemann sums if you want, you can think about anything, but either way, this should be 0 because there's no width to this. You can go back to our definite integral video and see that this is one of the properties of definite integrals, that if the limits of integration are the same, this area here is in fact 0. So what that means is that, oh, I've got a typo in all this stuff. This plus c is supposed to be on the other side. Whoops. So what that means is that this capital F of A plus c is equal to 0. And so we can solve for what capital F of A is. So if this is your property, or sorry, if this is your like family of antiderivatives, then each one is going to have an initial value of capital F of A being negative c for whatever that specific constant was. Now what we can do is take this and just go ahead and plug in negative F of A here for c, because c is equal to negative F of A. That means that for each of our family of, or each of our antiderivatives in that family of antiderivatives, we can link it back to this area function, one specific antiderivative, by subtracting the initial value F of A. Now this is going to lead us directly to the second part of the fundamental theorem of calculus, because we'll just evaluate this little expression at B. So that means then that this integral from a to b of f of t dt is a of b, because this is our area function again, from a up to x of f of t dt. And so if you plug b in for x, we've got the integral from a to b. And if you plug b in for x into this expression, it's just some antiderivative evaluated at b minus that antiderivative evaluated at a. Done. That's the proof of the second part of the fundamental theorem of calculus. Okay, so what does this actually mean? What this means is that evaluating definite integrals like these is actually pretty easy. First, find an antiderivative. Antiderivative. There we go. Spelling is hard. Notice we just have to find an antiderivative, one of the antiderivatives. Normally, I'm going to pick the antiderivative where that constant at the end is 0. But you can pick any antiderivative and you'll see that it doesn't really matter. Second, what you'll do is evaluate this little expression. Your antiderivative evaluated at b, that's our upper limit of integration, minus your antiderivative evaluated at a. All of these should be pretty easy then to do, because we know how to find general antiderivatives, and we can probably evaluate functions pretty easily. So let's do the first one, and then I'll let you do the second and the third one. I'll make you pause the video, or at least encourage you to pause the video, and we'll see what's going on from there. All right, so we need an antiderivative of 18x and 3x squared, and that shouldn't be too hard. We know that we're just going to be dealing with power functions, so we add one to the exponent and divide. Honestly, for stuff like this, if you've got some practice, you might be able to just look at it and tell. We're going to have 9x squared minus x cubed. Now, I could put in a constant there, but I'm just going to pretend there's like a plus 0. I'm going to evaluate this from 0 to 4. What that means is I'm going to plug in 4. So this is 9 times 4 squared minus 4 cubed minus, so this is when, this is my capital F of b, and then I'm going to say minus 9 of 0 squared minus 0 cubed. And this is my capital F of A. Oops, I wanted the same color here. So F of B minus F of A. And we just have to do some arithmetic. This is 9 times 16 minus 64 minus 0 minus 0, which is kind of nice. Let's see. 9 times 16 is 144, I think. Right? 10 times 16 would be 160. So 9 times 16 is just 160 minus 16. minus 64 minus 0. So I've got 144 minus 64. What's that? That's 140 minus 160. That's 14 minus 6 times 10. So we're looking at 80. Cool. So our area under the curve here is 80. I'm going to get rid of all this, so just to save some space, because arithmetic should be something that we can just crunch through. So this is 80. Now notice that if I wanted, I could add a constant onto these. Let's pretend that I put the constant 1 in here. Notice what happens. 1 minus 1. That's 0. That's going to happen for every constant, right? You could put a general plus c in here, and then you've got c minus c. But for the same antiderivative, you have the same constant, and so those always just subtract to 0. So we don't need to worry about that constant of integration here. You can just grab any antiderivative, and so I normally grab the 1 with that constant of 0. All right, cool. Let's take a look at this next one, and the third one maybe I'll give you a hint on. Notice we've got this beautiful little upside down triangle. So that means that we can really rewrite this integral as the integral from 4 to 9 of x to the half over x minus 1 over x. Oh, I forgot my differential on this thing. Whoops. Dx. And so this is really an integral from 4 to 9 of x to the negative half minus 1 over x dx, just by doing some algebra stuff first. That's going to make it easier to find antiderivatives for this last one. Go ahead, pause your video, see if you can take a look at these things, and we'll pick this up in a second to help out. All right, so hopefully we can see our antiderivative of 2 sine of x. We can use negative 2 cosine of x, and we'll evaluate this from 0 to pi, which is negative 2 cosine pi minus negative 2 cosine 0. So we've got negative 2 cosine pi plus 2 cosine 0. If we need some help remembering about what those cosine values are, you can draw a unit circle here. And remember, cosine is the x value. Cosine of pi then is negative 1. So this is negative 2 times negative 1 plus 2 times 1, because cosine of 0 is the x value here. That's positive 1. So we have 2 plus 2, which is 4. All right, so again, maybe I'll go ahead and just erase this stuff, give myself some more room. I'll say this is 4. And then in this last one, hopefully we can see our antiderivative. We have to add 1 to our exponent and divide. So this is going to be 2 square root of x, because it's 2x to the positive half, minus our natural log of the absolute value of x. And we'll evaluate this thing from 4 to 9. So we'll plug in 9 first. 2 root 9 minus natural log 9 minus 2 root 4 minus natural log 4. And so we've got 2 times root 9 is really 2 times 3, so that's 6, minus natural log 9, minus 2 times root 4, which is 2 times 2, so that's 4, and then it's minus negative natural log 4. 6 minus 4 is 2, and then if you want, you can combine these logs together and say this is really the natural log of 4/9. Or you could say natural log of 4 minus natural log of 9. Same thing. I'm good with whatever. But you can use some log properties, especially because I'm running out of room in this corner, so it's nice to just write this with 2 terms instead of 3. All right. So this isn't too bad. What you'll notice is that this just hinges on us being able to find antiderivatives, which initially we might think is a good thing because, excuse me, if we go back to earlier, I said that the first part of the fundamental theorem of calculus is the thing that really tells us that if you have a continuous function, you're guaranteed an antiderivative. We had this idea of integrable functions earlier where areas might exist, but now specifically we can say, I know that antiderivatives exist for functions that are continuous. And here's our reality check. Not necessarily easy. We do know that antiderivatives exist for every continuous functions. And we do know that the second part of the fundamental theorem of calculus says that once we have that antiderivative, we can just evaluate capital F of B minus capital F of A, and we're good to go. The problem is, just because an antiderivative exists, that doesn't mean it's easy to find. Maybe I'll be more specific. It doesn't mean that we can write it down easily. So here's the quick little summary. We know that if a function is continuous, then it has an antiderivative, and specifically we can use the area function. One of the antiderivatives looks exactly like this for some function f that's continuous. That's not a guarantee, though, that it's an elementary function. We may not be able to write it down specifically just using basic function types and combinations of those things. For instance, if we wanted to do something like this, I'll just do x squared for now. This function does not have an elementary antiderivative, meaning I cannot write this down as some capital F of x plus c, where capital F of x is like a basic function type. If you wanted, we could write it down by saying, okay, it's the area function. Plus some constant of integration. But that's not actually that helpful. We might want an actual explicit elementary function type to do this. So there are a whole bunch of functions that have antiderivatives, right? They exist. There is some function that you can differentiate to get that function that you care about, but it's not a basic function type like combinations of exponentials and trig functions and polynomials and logs and coefficients and all that kind of stuff. So, a little disappointing. All that to say, integration, antidifferentiation is difficult, but if we can find an antiderivative, finding areas under curves isn't hard. All we have to do with that antiderivative is evaluate it at endpoints. So the hard part is still in the antidifferentiation. And that's what we'll spend the last chunk of our class together talking about. How do we find antiderivatives for some of the difficult functions? There are a bunch that we won't be able to get to this semester, and we'll spill into our Calc 2 topics. That's where we spend a lot of time going over integration methods. And there will be some, like this e to the x squared, that we'll never be able to find an elementary antiderivative for. But there is still hope for it, because maybe we can play with some other stuff to get versions of things that can be representing antiderivatives. You can see what that means if you sign up for a Calc 2 course or take a look at some of my Calc 2 videos that I've got on my YouTube channel. All right, that's everything that we've got for this. So go practice, have some fun with the fundamental theorem of calculus. We're going to care mostly about that second part, evaluating definite integrals. And it should be really nice to see that these are mostly, when you're looking at examples like this, mostly pretty easy to do. So have some fun with that. Don't worry so much about having to worry about Riemann sums and limits and all that kind of thing, because this second part of the fundamental theorem of calculus saves our butt on that. All right, good luck, everybody.